I'm Klaus Pontoppidan, the former JWST Project Scientist at the Space Telescope Science Institute. And I'd like to tell you about how we created the first color images with the James Webb Space Telescope as part of the early release observations that were released right after commissioning of the observatory. So this is Roskilde Cathedral. It's a Gothic cathedral. It's located right outside Copenhagen. Back then, these Gothic cathedrals took a long time to build. In this case, more than 100 years. And we know that the builders and the architects back then knew that they wouldn't see their creation finished in their own lifetimes, yet they persisted and they still built the cathedrals those days for the glory of God. Today we're making other types of generational projects that we do because we are now technologically able to, and these projects, these scientific projects, are able to, in a new way, tell us about our origins, where we're coming from, where we're going, and to open up some of the deepest mysteries of the universe. And the James Webb Space Telescope is certainly one of those. And it's truly generational in that it took 25 or 30 years from the original inception until we were able to launch it, and until it could return amazing science and beautiful imagery. And we had to do this in an environment where people's attention span is short, and where a lot of us live through our mobile devices, and where the news cycle is incredibly short. So something that takes 30 years to build, you may only have a few hours to make your point that it is an amazing facility and worth doing. And so this was the place we were in when the final testing was being done on the James Webb, here seen out on Redondo Beach at Northrop Grumman during one of the final tests of the Sunshield deployment, not long before launch. So basically, we were tasked as a team that were to create the first color images to answer this question: was it worth it? It was worth it. So these were big shoes to fill, and we were very well aware of that. And so the creation of the first color images was a very serious task that was project managed for years leading up to that event, and it was one of the key or core activities during the 6-month-long in-orbit commissioning of JWST. So the objective of the first images was to create spectacular images worthy of a flagship observatory. So what is typically known as the first images is also known as the early release observations, and this is something that is very often, if not nearly always, done for a new astronomical observatory, space observatory. The early release observations were not intended to be necessarily scientific. They were intended as a public outreach product to showcase the observatory, but were not designed by for the basic purpose of doing science. And everything else that comes after that generally is for science, but the EROs, the early release observations, were not. They were to include observations from all 4 science instruments, because there were key contributions from different partners, not just NASA, right, but the European and Canadian space agencies made foundational contributions to James Webb, and so those all had to be highlighted for obvious reasons in the first release, so on. And one of the big objectives that we often heard back then was that, we should appear above the fold in the New York Times. Of course, nowadays nobody reads a printed newspaper anymore, and so what does it mean to really be above the fold? But at least, on the top of the primary product of major newspapers like the New York Times. So JWST was originally built with one science case in mind, although others followed later, not least the characterization of exoplanets, few of which were known in the mid to late 90s when JWST was really originally conceived of and designed. So the original case was to find the first galaxies in the universe and understand their early evolution. And this was done because at that time there was the Hubble Space Telescope was operating, but it was understood that the Hubble was not able to see the first galaxies. The reason being that Hubble is primarily an observatory that works at optical wavelength, visible wavelength, a little bit in the ultraviolet, a little bit in the infrared, but not much. And galaxies that are very far away, their light had to travel to us for a very long time. And as light travels through the universe expands. I mean, the universe expands all the time. So the light expands along with the universe, and light that expands gets, so to say, stretched. It gets longer wavelengths, and light with the longer wavelengths is redder. And so very red light becomes infrared light. It translates out of the visible spectrum so that Hubble is no longer able to see it. Put it another way, old light is red light, and very old light is infrared light. And so it was understood that in order to see these galaxies that are very distant and whose light has then traveled for a very long time requires an infrared telescope like the James Webb. And so what is seen here is the famous Hubble Ultra Deep Field, where Hubble stared at a tiny patch of sky for as long as they could get away with, which is about 2 weeks of exposure time. And basically every point here you see is a galaxy, most of them quite distant. There's only a few stars in the foreground in our Milky Way here. Everything else is in the distant universe. And so a lot of people were, of course, waiting to see what an image like this would look like with JWST. And so it means that James Webb is operating in infrared. And the infrared wavelengths is actually a larger fraction of the electromagnetic spectrum than the visible. The visible light is a tiny little bit of fraction. It's a bit exaggerated in a weird way in this infographic here, but you get the point. So put it another way, there are more infrared colors accessible by JWST, many more in fact, than exist in the visible range. And so when we had to make pretty images, beautiful imagery with JWST that would rival or get even better than those that people were familiar with from Hubble, we have a lot of leeway in how to do that. Right? And there's also questions about how to translate what is essentially invisible light into visible wavelengths, and to translate the richness and complexity that we expected to be in infrared because there were so many colors available. We just didn't know necessarily what that would look like in any great detail, and attempts to model it or simulate it always sort of turned out unsatisfactory. So that was one of the challenges we had. So nevertheless, we proceeded, and the way that the early release observations were arranged is that there was what's called a selection committee that existed between 2016 and 2021, with committee members that you see here, representatives from the different space agencies, and with a lot of representation from the Space Telescope Science Institute. And what essentially was done was you started with a lot of the great hits we had from Hubble, and then tried to think about which ones of those would be most appropriate for James Webb, taking into account the different circumstances of that telescope. Here to the right here you see the early release observations from the fourth servicing mission from Hubble, and so that was sort of the benchmark that was set up in those days. This committee ended up with a selection of about 70 potential targets, and they couldn't actually get closer than those 70 to the few targets that we ultimately ended up with. And in a big part, this was because of the special orbit of JWST, where JWST could only see about 20% of the sky at any given time. And so because we didn't know exactly when launch was going to be, so we didn't know when the early release observations could be executed, we had about 120 hours worth of time to use for the EROs. We had to essentially make a prioritized list, and then depending on when the observatory was available to us, we'd pick the best targets accessible to us at that time. And so that's what we did. So there was essentially a script that we could go through, and so depending on now we have time to do our observations with this instrument, which targets are available, and then go down the list in that way. So once we got to the end of commissioning, we put together an implementation team. This is the names on the implementation teams. This is a paper we wrote to describe the EROs after they were released. And these were 30 or so incredibly talented experts in all sorts of different fields, right? So there were scientists here, but more importantly, there were imaging specialists for public outreach, had a lot of experience with creating color images from Hubble, education specialists, writers, and of course scientists with instrument expertise as well. And we had to be very efficient back then, because we only had a short amount of time available to create the images, 6 weeks in fact, from the first instrument becoming available for this kind of observation until we had to release the images to the public. And it's not very much time, considering the 4 instruments. We had to build in redundancy. We had to reduce and process data that nobody's ever processed before in this kind of context. Obviously, early on in commissioning, data had been taken, but never with the intent of producing something. All right, so what are some of the considerations that went into creating the images? I think a key one here is that while James Webb, of course, is an amazing observatory, it's the largest infrared observatory ever flown, with amazing spatial resolution to match incredible sensitivity. You have all those things going for us. But when you make an image to the public, one of the key things that matters is actually not so much the resolution of the observatory, but how many pixels you have available. Right? So when you just see a space image, you don't necessarily care about how large the image is on the sky. And that's what resolution means for something like James Webb, is you can take images of tiny patches of the sky with great detail, but it can be equivalent. You can have equivalent aesthetic quality to have an image of lower resolution that just is of a larger part of the sky, so in such that you still have a large number of pixels. And so essentially what we were going for here is to have a lot of pixels available, and you knew that would create a spectacular image, actually, regardless of resolution. So it's just one of those things. And so we're going for Ultra HD, so 8K images, so about up to 10,000 pixels on the side. So one advantage of James Webb is that it's eminently capable of doing that. Its near-infrared camera has a very large amount of pixels available to it, so it'll generate these images fairly quickly. So here's an example of that. So this is not from James Webb. This is from the Herschel Space Observatory. So that is a preceding infrared observatory that was led by the European Space Agency. And the image on the left is of M51, a nearby galaxy. which there was one of their early release observations. And you can see it looks fuzzy, and that's not because Herschel was not a large observatory, it's just because this was an object that to Herschel was not that large. And so there are not many pixels across it. To the right is another Herschel image that was obtained toward the end of that mission, with many more pixels available. You can see it just looks sharper, but really it's not any sharper, it's just a larger object on the sky. And so it just looks much, much better. Another thing that was important to us was photographic composition. And so this is just applying normal photographic compositional techniques to astrophysical images. And here it was a real advantage that we didn't have a scientific objective. We had an aesthetic objective. Because scientific images, or images that are taken for scientific purposes, often not, you don't have to compose them as a photographer. And so they're for that reason alone, they're often not as good. It's not always the case, but they're often not as good for public outreach because you're just not intended for that. So here, and I'll go into more detail about this particular image, the famous cosmic cliffs near the Carina Nebula. So that I set up to show this mountainous landscape. It uses a filter that detects emission from complex hydrocarbons called polycyclic aromatic hydrocarbons. This is at a wavelength of about 3.3 micron. And the reason that we're using those is that we knew that because of a combination between the kind of light they absorb from stars, ultraviolet light, and the kind of light they emit in the infrared, and the kind of chemistry that they trace, that they emit from this very, very thin layer in this cloud, this very thin transition layer. So it makes a very sharp transition, which is something that takes full advantage of the resolution of James Webb. So you can end up with this very sharp mountainous landscape by picking that particular filter and then adding other filters on to create the colors here. So you can get this kind of blue sky and the reddish brown mountains underneath. And then you set the composition such that your ridge is along the long axis of the camera, so you get this kind of landscape effect. And you place the ridge close to the golden ratio. So it was actually done deliberately in this way. And it turned out to be very popular. I mean, it's a very popular desktop image, I would say, these days. It's a young star forming region, and there's lots of other stories to tell about this area. But it was composed for the color contrast, for the brightness contrast, and for our ability to create this kind of standard, or classic, or say, photographic composition. Another thing that we knew then, and I guess you sort of tend to learn over and over again, is that you actually have to use a fairly limited spectral range for your image. If you use colors that are too far apart, the resolution is too different, and they tend to pick up completely different physical processes, and so they look like they're put together in an unnatural way, right? We are going for a natural feel, so that requires us to keep the wavelength range that we cover fairly narrow. And so here's an example of where this doesn't work well, just at least to create a natural photographic feel here. So here's just a combination between Hubble images and an X-ray images. Completely different wavelength ranges, tracing completely different physical processes. And so you end up with this sort of fuzzy nebulosity and very sharp galaxies in between. And it just look like it's almost like an error that you put something together that doesn't match. Right? And so this is true for JWST as well, because the wavelength range is so wide. So often if you try to put together images from NIRCam and MIRI, they tend to look a little unnatural. And so we experimented with that, but tend to always find that the aesthetically most pleasing images are the ones that use one instrument. The next thing, which is very typical for this here, and is a key way that we translate, say, infrared imaging into the visible range that we can see with our human eye, and that's chromatic ordering. And what that basically means is that the shortest wavelength of infrared light gets mapped to the shortest or bluest visible light channel, right? So it becomes, you don't mix them up, right? You don't make a red infrared color into a blue visible color. And this is what creates an actual translation, like translating a language. And so here's just some examples of where you can actually see the colors that are assigned here for the cosmic cliffs to different wavelengths, and you can see they follow the chromatic order. Finally, it's a bit of a technical point, but it was something else very important to us, and that was to make sure that you have high signal to noise everywhere in your image, right? So that your exposure time is long enough that they reveal all the details and not just noise. And you'd think that James Webb is a very sensitive observatory for this kind of extended nebulous emission that it becomes so pleasing in an image, but it's not, in the sense that it's a very large mirror. It collects a lot of photons, which is good, but that image gets projected down onto very small pixels. And so when you have all the photons available and you divide it out between all the pixels, there's not that many photons per pixel. And that's a lot of what creates your signal to noise, that you have enough signal to not get graininess. And so as an example here, we're comparing to Spitzer, which had a much smaller primary mirror but had much larger pixels. Actually, it turns out that Spitzer collects about significantly photons significantly faster per pixel, because the pixels are so much larger, and compared to, even though the primary mirror collecting area is smaller, the pixels are larger. It's bigger buckets, let's say. Put it in another way, we still had to use very long exposure times with JWST to get good signal for these images. It's another reason, by the way, that's images taken for scientific reasons are typically not as good, because they underexpose a little bit. They expose as long as you need just to do the science, but not necessarily to get a clean, grainy-less image for a nice color image. So here are just some pictures of this process ongoing with the implementation team. The upper left here is actually the moment. It looks staged a bit, this image. It was a moment that we're seeing the first images. I'd seen them already, downloaded them, but others had not at that point. And some of the other images from the production, actual discussions of details in the composition of the images, and us some of us at the bottom with an example of one of the images. So let me just go through here, just give you an example of what the Carina or the cosmic cliffs look like as they're processed here. So this is the way they actually come out of the camera. So this is one exposure, and you can see how a detail of the cosmic cliffs here emerges from the fog as the observatory is collecting photons. And there's lots and lots of complex instrumental noise and other things on top of this. So that can be cleaned up fairly well here. So here's that image cleaned up with all the instrumental noise removed. And you start to see the real structure here, but you can still see a lot of missing bits and pieces, and that's just typical for this kind of data, or this kind of camera. And so what you do is you actually collect a lot of images here. For the cosmic cliffs, there was more than 700 individual images that all had to be stitched together in a seamless way. So you can see this is a detail of this called mosaic that gets put together. And then this is a full field of view just in this one filter here. So this is the PAH, the polycyclic aromatic hydrocarbon filter at 3.3 micron. And then you take all the filters, you put them together, and that's really what creates the color image at the end. So I mentioned in the beginning that one of the key science cases, or the key original science case for James Webb, was to detect the first galaxies in the early universe. And we weren't actually really supposed to do this as an early release observation, because this is something that you'd spend a lot of time on to go really deep and see these very, very faint galaxies. But when I did the calculations back then, I realized that if you just spent 7 hours with James Webb, we would easily surpass, actually go quite a lot beyond the sensitivity of the original Hubble ultra deep field that took 2 weeks. And so we're just kind of like, okay, we should just do a deep image as well for the early release observations. And this is what it was. So here we pointed it at a galaxy cluster, which has the added effect that its immense gravitational field around this massive galaxy cluster also acts to focus and intensify the light from distant galaxies behind the cluster. So it's called a gravitational lens. And you can see that effect as this kind of stretchy arc structures around the galaxy clusters in the middle. And so you're just able to see faint things that would otherwise be too faint to see even with James Webb if the cluster hadn't been there. And so this certainly was at the time the deepest image of the cosmos obtained. It's been surpassed by now, but not by that much. So still pretty proud of being able to do this early on. This was incredible to see this image as it first came down. And you can zoom in. There's so much detail in these deep images with James Webb. And you can see individual stellar clusters in these distant galaxies that are being lensed and magnified by the intervening cluster. Ultimately, the release was a great success. We had about 200 billion impressions that day, and an impression is a measure of the impact in public outreach, and it's just an opportunity or a chance for anyone to see the images, whether it's in a newspaper, or on social media, or on the news, or wherever. And so 200 billion impressions just means that every person on Earth had many opportunities to see the images. And so you can see they were displayed in public squares, and they were in Times Square and Piccadilly's and so on, the images. And you can see the in this case, of course, the cosmic cliffs. And we did make the cover of the New York Times. Actually, not one day, but 2 days in a row. One of the really fun things, of course, was that a few days before we heard that the White House was interested, and so President Biden did present the first image, and that was that deep image. That was the first image they wanted to show, and it was funny because it was kind of one that we weren't originally supposed to do, but we did anyway. And then at the end of that, at the end of many media interviews and lots of activities and festivities around that, of course, we settle into more of a routine with James Webb, which is now just churning along and producing amazing science every single day. Incredible data coming down, so many discoveries on the way. I've seen amazing things in the literature and amazing things being put out. But in terms of public outreach, we do have to keep going and not just leave it at that. And so we were fortunate enough to be allowed to do that. And so we actually had a season 2, so to say, the Cycle 1 outreach campaign. And so I got to put in some targets in here that we wanted to, I guess I wanted to do as early release observations, but we didn't for various reasons, whether it was visibility or for other reasons. But there were some really interesting things we could do for public outreach reasons. One was the pillars of creation, which you see here on the right. You see this is one of the planning setups where you plan the composition of the observatory on the sky, and the scripts that you send up to the observatory to execute. We didn't do the pillars of creation for the EROs because we thought it was too iconic. It was such an iconic Hubble image. But on the other hand, everybody was asking for it. There was a lot of people like, oh, they were speculating, we're going to see the pillars of creation in the early release observations. So we kind of had to do it. Another thing I noticed was there was no NIRCam image of the ice giant Uranus and Neptune in the first cycle, so we had to do that as well. And there's a number of star-forming regions that I knew would be really, really nice that are not visible to Hubble or at visible wavelengths at all, right? So be very unique to JWST. So I really wanted to get some of those in there where there's no Hubble equivalent. So to have something that's really truly unique for James Webb. So of course this is what we came up with for the pillars of creation. Where with Hubble you don't see all these background stars here, but in infrared the light gets through the intervening dust, and you see right through the nebula, and you see all this multitude of background stars, and it gives a very different feel to it. So in terms of galaxies photobombing, one of my favorite things here is I wanted to, for the ice giants, not just take an image of the ice giants themselves, but put them in context of the distant universe. And I think it's the first time this has been done. It took a little bit of work because the brightness difference is so different. This is a huge dynamic range kind of image. So this is Uranus and its moon systems. You see a bunch of moons here. They're very blue because they're very icy and reflect light in a very blue way in the infrared. And so they're very obvious to see what is a moon here because it's so blue. And then you have this background galaxy field of reddish galaxies, but you get a feel for the size of the planet itself as seen from JWST, which is not that far from Earth in this context, and the size of the background galaxies here. So it just puts our local backyard into the context of the distant universe, and I really like that sort of story that we could tell there. And then, so this is not a JWST image, it's a Spitzer image, but it's one of my favorite regions. This is the OAE star forming region, the nearest young star forming region to us in the Milky Way. So this is where we can get the most amount of detail. This is a huge field, so we can only take an image of a small field here. So this is what I picked because it has this trinity of stars up to the right, and this region of complex organic emission that is excited by one central star in the middle here, and I thought that would make a great composite image for James Webb, and it did, and so we ended up using this as a first anniversary image, and you can see what is a bit of a surprise, maybe not a complete surprise, but the size and complexity of this perhaps was a surprise. All these red structures which are outflows, giant outflows from individual young stars that are currently forming here, and they blow through the cloud here in these massive structures. So almost every star you see here is a young star in this region that's not too different than a solar mass, maybe in some cases a little bit less. And so that's sort of the end of my story here for the first images. We were able to put together first images in the EROs, and we were able to continue that tradition for James Webb, and I think it will continue for many years, just like it has for Hubble. This is an amazing observatory, able to produce fantastic science as well as to excite and intrigue the public. And with that, I'd like to thank you for your attention.